Okay, all right. So, today is going to hurt. I promised you last time that we would end before spring break with sort of an analysis of the Schwarzschild solution, which I was corrected by a viewer on YouTube that I've been misspelling that for my entire career.
That guy's been commenting misspellings on so many things, like the same person.
Yeah, I'm pretty terrible with spelling. And what's funny is I think I've taught this course for so many years and no one has ever corrected my spelling on that. And maybe I was at one point doing it right and then just copying something down, I dropped an S, but anyway, so it's correct henceforth. But anyway, we did look at this Schwarzschild solution and we looked at how that gives us some predictions which are different from Newtonian gravity, hence gives us potential ways to test general relativity, whether or not it's correct. And we finished up with the calculation of the precession of perihelion of Mercury, which was one of the first tests of general relativity, quantitative tests. And so what we're going to do today is go through the wonderfully illuminating exercise of actually figuring out where that solution comes from. Okay? Jason, get off your phone.
Oh my gosh.
Man, you are so absorbed in that thing. Okay. So we will seek. So this is going to start out much like finding solutions to differential equations in, say, E&M, or in other contexts where you say, okay, in general, the solution to the equation could be horrible, but if I assume certain symmetries, then maybe the calculation or the solution will be a little bit easier to obtain. So what we're going to do is we're going to seek spherically symmetric solutions. To Einstein's equation. For two reasons. Okay? One, they are easier. Okay? Clearly, from your experience in, for example, E&M, when you assume a spherically symmetric, configuration, then you've got to automatically make assumptions about the form of things. And I'm actually going to do a very quick review of an E&M calculation to get things started. So you know that it makes things easier, but the good thing about gravity is that if you think about large objects, for the most part, they are spherical. Okay, if we think about stars, if we think about planets, they are, to leading approximation, spherical. In E&M, you know, you could have a wire, you could have a plate, okay, you can have all kinds of weird geometries in E&M. And so in general, you find yourself sometimes using cylindrical coordinates, sometimes using spherical coordinates, sometimes using rectilinear coordinates. But in GR, really and truthfully, the first thing you should try and look at is spherical solutions. Okay, guys, don't focus on your exams. Pay attention to the front. You'll have plenty of time after class. But clearly for astrophysical sources, spherical symmetry is the way to go, and we'll relax that a little bit later. And the only place in GR where we really get away from spherical geometries is when we talk about the entire universe. Okay? So this is telling us it's going to be easier, and this is telling us we're actually not losing a lot of the utility by making this assumption. So what I'm going to do to start is review the procedure from E&M, because this is going to kind of give us an idea of what the story looks like in a much more concise format. So let's consider Gauss's law. And so I'm interested in solving in electricity and magnetism. I'm interested in solving for the electric field associated with a time-independent spherical source of charge. Okay? So this could be a point charge or it could be a sphere of charge, as long as it's spherically symmetric. Okay? So Gauss's law is one of Maxwell's equations. It's the differential equation that we can use to solve for the E field given a charge distribution rho. And then here's the part which gets confusing. All right? If I imagine that there's some source of charge, and it could be a point, it could be whatever, I want to solve for the electric field outside of it. Okay? So I would like to know, what is the electric field located here? Now, for those of you who've only seen the electromagnetism in Physics 200, you're used to working with Maxwell's equations in their integral form. Okay? But the differential form is the form that you typically see outside of the context of Physics 200. And what's important about the differential form of Maxwell's equations is that they are local equations. They hold at each point in space. And in time, for that matter, if things are varying in time. Okay? So here is the critical question. I have a charge distribution here, contained in the sphere. I want to know the electric field right there. Let me pull a card at random. Oh, it's Jonathan. Let me shuffle them.
Oh, man.
Jonathan, what should I put on the right-hand side of that equation if I want to solve for the electric field there?
KQ over R squared? Yeah. Just KQ over R squared.
So this is a differential equation which holds locally. That is, each side of the equation is talking about what's going on at that location. I want to solve for the electric field at that location. That'll be from the left. The right-hand side is the charge distribution at that location. What is the charge distribution at that location?
0.
It's 0. So what we actually want to solve, if we're outside of the source of charge, is that equation. Okay? Now, if we assume spherical symmetry, and we work with spherical polar coordinates, which are the coordinates most naturally adapted to exhibit spherical symmetry. Clearly, from your experience in other contexts, you know X, Y, and Z is not the way to go if things are spherically symmetric. But if we work with spherical polar coordinates and we assume spherical symmetry, then we can immediately write down a fiducial form of the electric field. Let me draw a card at random. Jonathan. Imagine that. Jonathan, in what direction must the electric field point?
Radial.
Radially. Good. So it must be proportional to r hat. Okay? Now, it's proportional to r hat, and the thing that sits out here is going to be the functional dependence that tells us how it changes when you move around. Which of those three coordinates is this going to be dependent on?
R.
R. Good. Okay. So just by making the assumption of spherical symmetry, we can automatically conclude that the electric field only depends on R, and it only points in the R direction. Right? Okay. So if we now take this and we shove it into Gauss's law, then what we have is the following. First of all, we have to write Gauss's law in spherical polar coordinates, which, you guys, put your tests away. I know you're very excited, but you need to pay attention to the lecture. Is that one that didn't get picked up?
Yeah.
Okay. All right. You guys are killing me. All right. So we got to write the divergence operator in spherical polar coordinates, which you all know now understand the machinery of how you get to these expressions, but just reminding you the form of it. We have 1 over r squared, partial derivative with respect to r, of r squared f of r, and this has got to be equal to 0. Okay, now if you don't remember this, that's fine, but you could go through and you could calculate the Christoffel symbols for the spherical polar coordinates in flat space, and then you can construct the covariant derivative, et cetera, et cetera. That's the expression you end up with. There are usually more terms, but since we know things only depend on r, and they only have an r component, it simplifies to this. And now looking at the the term here, we notice that this thing 1 over r squared is not going to be 0, okay, because you're some distance r from the origin. The origin is at the center of the spherical distribution. So this coefficient is not 0. So in order for the whole thing to be 0, I need this term to be 0. Okay? Jonathan, so lucky today.
Yeah.
If I want the derivative with respect to r of this thing to be 0, what do I need this thing to be?
1 over r squared times the constant.
Sorry, the whole thing in parentheses.
Oh, a constant.
A constant, okay? So this tells me that, and you can continue what you were saying, it has to have what form?
1 over r squared. Or constant over r squared.
Good, it has to be of the form of a constant over r squared. Okay? So if I have k over r squared, I could add, oh no, I actually couldn't add a constant to it. K over r squared, the r squareds cancel, I'm left with a constant, the derivative of that with respect to r is 0, I'm good to go. Okay? And so this is now telling me that my electric field behaves as k over r squared, but I don't know what k is. Okay? How are we going to figure out what k is?
Boundary conditions.
Say it again?
Boundary conditions.
What were you going to say? Boundary conditions?
Boundary conditions.
So how do we figure out boundary conditions?
Well, you can take, one boundary condition is that the electric field should vanish as it goes to infinity.
So that is not going to help us determine k.
Then you can use the boundary condition at 0.
If you're using the boundary condition at 0, and this is an extended distribution, then you're inside of it, and this solution doesn't hold anymore.
Boundary condition at the surface.
Say it again?
Boundary condition at the surface.
How are we going to apply the boundary condition at the surface? What is that going to look like?
We say the E field at the surface is a thing.
So does anybody remember how this argument plays out in your E&M class? You should have seen this, I think, in intermediate E&M, at least in the differential language.
You have to match 2 solutions.
That is actually an important criterion when you're trying to construct the interior solution, and then you want the interior solution to match up to the exterior solution as you take r to the actual radius of the object.
Is this the parallel, perpendicular stuff with everything and how it all has to match?
No, that's in the.
Do you look at like the D field and the H field? No.
You say the total E field at any radius will be the same,
The charts.
like across the whole spherical area?
Okay, yeah, so there's an ingredient which you all know comes into the story, but you might not be remembering exactly how. So what you do is you say, okay, I'm going to construct a spherical surface that extends out to this point. All right? And then what we're going to do is we're going to integrate both sides of Gauss's law. So I'm going to integrate both sides of Gauss's law. That's this form of it. Okay. When I integrate the right-hand side over the volume of this sphere, what do I get?
Total charge over epsilon.
Yeah, you get the total charge enclosed over epsilon naught. Rho is the charge density. If it's a uniform charge density, it's the total charge divided by the volume. But at any rate, if I integrate over this entire volume, I'm going to end up with the total charge enclosed. And then what we can do is we can use the divergence theorem to turn this into an integral of the electric field dotted with an infinitesimal area element. So the divergence theorem is the piece that you bring into the story, because the divergence theorem takes you now to the integral form of Maxwell's equations, and the integral form of Maxwell's equations are not local. They actually care about adding everything up over volumes or areas. Okay? So if you're just working with the differential form, you're not really going to have this information about how this directly couples to this. You have to kind of convert to the integral form so that you're actually looking at the whole story, okay? And then we know how this plays out. When you do this integral, you know that the electric field is parallel or anti-parallel to the infinitesimal area vector. Okay, if we use an outward pointing area. And so this dot product simplifies into just an integral of E dA, and then you integrate over A, and then you just end up with 4 pi r squared times the magnitude of the electric field, which is Q enclosed over epsilon naught. And so we can say that the magnitude of the electric field is Q enclosed over 4 pi epsilon naught r squared, and you'll notice that gives us our value of K. K is Q enclosed over 4 pi epsilon naught. Okay? So at the end of the day, our electric field looks like that. Okay? All right. Now, everything that I've just said would be the exact same answer no matter how big or small this is, as long as I'm outside of it, and as long as this thing is spherically symmetric. So it could be a point, it could be a spherical shell, it could be a volume of charge, it could be a volume, it could be an object with a charge density that varies as you move along the radius, as long as it's spherically symmetric. All of those are going to give you the same answer. It's just going to be the net charge enclosed over 4 pi epsilon naught times whatever r squared. Okay? If, however, we decide that we want the solution there, okay, that is, we have an extended volume of stuff and we want to know, well, what's the charge density inside of it, then we actually have to solve this form of the equation because the charge density is non-zero, and that will give us what's called the interior solution, which, somebody mentioned it earlier, Alex, I think, which we can then match to the exterior solution. Okay. Now, for what we're going to do in this class, we are going to start by assuming that we are outside of some mass distribution, and we're going to be interested in solving for the geometry outside of it. So we're going to get an exterior solution. Next time, we're going to extend that to interior solutions. And the main reason why we're going to focus on interior solutions, they are technically way more complicated, but the main reason we're going to focus on them is because it is only through studying interior solutions that you can get to the conclusion that black holes are predicted by general relativity. So I wouldn't go there unless you get something really cool out of it. Okay? But for today, we're just going to be focusing on the exterior solution. So are there any questions about this E&M review before we push on to the nasty stuff?
I wish you had wave jackets.
I didn't say nasty, I just said nasty stuff. Okay, so a couple of things to note. We were actually solving for the electric field directly. We could have instead asked to find the electric potential, and then from the electric potential we could have gotten the electric field, okay? So we could have instead written down the equation governing the electric potential, but when we solve the equation for the electric potential, we have a tool at our disposal to help us solve the problem, and that is, for the electric potential, you can do gauge transformations, okay? We didn't run into that here because we went straight for the throat with the physical E field. I bring that up because in general relativity, we're actually going to be solving for something a little more like the potential, so we're going to have the flexibility of making gauge transformations. Okay? Now, what are gauge transformations in general relativity? Let me pick a victim. Oh, it's Jonathan. Okay. Jonathan, what are the gauge transformations we encounter in general relativity?
I don't know.
You don't know? Wow. I think I sent it in that email that you never responded to.
Oh.
Or maybe it was the second one that you didn't respond to.
I remember the first email.
Yeah, I didn't send it in the email, dude. Stop looking. So does anybody want to tell them what the gauge transformations in general relativity are? They're coordinate transformations. That's the first thing we talked about in our last lecture. Okay. Coordinate changes are the gauge transformations we can use in general relativity. And we're going to use them extensively. Now, another comment to make before we jump into it is solving this is, of course, much easier if we start with spherical polar coordinates. If we started with rectilinear x, y, and z coordinates, you could do it, it's just going to be way, way nastier. Okay, so picking the right coordinates to start with can help the situation. And when you're working with potentials, you still have the freedom of making gauge transformations. In E&M, gauge transformations and coordinate choices are different things, but in general relativity, they're all lumped together because coordinate transformations are gauge transformations. Okay, so without any further ado, let's get into Einstein's equations. And see how it goes. All right. Shuffle these real good. Okay. So we want to solve Einstein's equations with T mu nu equals 0. That is, we want to be outside of the thing that's creating the curvature. We want to be outside of the planet, outside of the star. Okay? Well, if you're outside of it, then the energy momentum tensor where you are is 0. Okay? Now remember that Einstein's equation we can write in this form, which is the standard way to write it. Okay? So if we're outside of the object in question, we can set the right-hand side to 0 and then solve the left-hand side equals 0. But you might remember that last time we actually wrote this in a slightly simpler form by taking the trace of both sides and then writing this in what's called the trace reverse form. We talked about that in the last lecture. You can look it up. But the trace reverse form is going to be very useful to us today because in the trace reverse form, Einstein's equation takes this form, T mu nu minus 1/2 G mu nu times the trace of the energy momentum tensor. Okay? But since our energy momentum tensor is 0, its trace is 0, so the whole right-hand side is 0. Which means that the equation, or the form of Einstein's equations that we're actually trying to solve simplifies radically to that. That is, the Ricci tensor vanishes. Now, you know, this is the price you pay as you get more and more advanced in physics. That looks like a simple equation. It is not. Okay? R mu nu is built out of derivatives of the Christoffel symbols, which are built out of derivatives of the metric. And so if you unpack this thing, it gets really nasty. Okay? Eventually we'll get there. But for now, let's see what we can do. All right, so our metric, G mu nu, ostensibly has 10 independent functions in it. All right? And if we actually listed those, we would have, first of all, the diagonal components. Okay, I should stipulate. Because we are going to be looking at spherical symmetry, it is natural to adopt something like spherical polar coordinates. Okay? Now, one thing I want to go ahead and say to you is the following, and you're going to see this play out in the course of our discussion. Just because I'm picking these coordinates to start with, it doesn't mean that that's the coordinates I'm ultimately going to end up using for the solution. For the following reason. These coordinates, spherical polar coordinates, and you just tack on the time, those are coordinates which we are comfortable and used to using in flat space. You use them in E&M a lot. Okay? However, this geometry is not going to be flat. So the form of these coordinates are not going to play exactly the same role that they do in flat space. So at the end of this discussion, we're going to have something that we call TR theta phi, but we don't want to call them spherical polar coordinates because that sort of implies that they're coordinates on a flat space, which this is definitely not a flat space. Okay, so just keep that in mind. But in the set of coordinates, the metric is going to have diagonal components, which are the TTR, theta, theta, phi, phi, and then a lot of cross terms. And yeah. How many do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay. Let's see. Oh, Jonathan. Why don't I have GTR?
Isn't it the same?
Yeah, it's the same. The metric is symmetric. So if you know GRT, you automatically know GTR. Okay? So what I have in mind here is if you wrote down a 4x4 matrix and you said all of the elements, well, first of all, if you said it's symmetric, and then all of the elements are right now unknown functions, these are your unknown functions. Okay? And all of these can depend on TR theta phi. All right? So you have 10 unknowns, 10 unknown functions of 4 independent coordinates. All right. Here we go. So if we consider spherical symmetry, then we can actually go ahead and simplify this story dramatically. And so to impose spherical symmetry, and I want to, so I'm going to kind of break the method to the madness today down into 3 steps. Okay? So step 1 is to impose spherical symmetry and see what simplifications we get out of that. Okay? Step 2 is going to be to utilize gauge or coordinate transformations to simplify things. And we're going to do that a lot, and this step is going to annoy you. Okay? And then last but not least, and this is we're going to do a lot of work before we even get to this step, is we're going to apply the actual equation we want to solve. We're going to do a lot of work without even looking at Einstein's equation. Okay? And at the very end, we'll come back to Einstein's equation. So to impose spherical symmetry on our solution, what we can do is we can assume an S2 foliation of space-time. Okay, so what do I mean by that? So a foliation is a fancy schmancy word that really means take a space, like a volume, and break it up into sheets. Just like an onion can be broken up into the layers of the onion. Okay? And those layers all taken together create the volume of the onion. Okay? So for example, if you have flat space, a natural foliation of flat space could be in terms of planes that are just stacked together along, say, the z-axis. That's a foliation of R3 into R2 planes. Okay? What we're doing in this case is a little bit more like the onion analogy, and that is we are considering just concentric spheres of smaller and smaller radius, which are stacked along the radial direction. Okay? But it's a little more complicated than that because we also have time. These spheres sit in 4 dimensions. So in the radial direction, we have these spheres stacked in order of increasing radius, but then in the time direction, we have copies of the sphere just lined up along the t-axis. So pick any one of these S2. So S2 is just a 2-sphere. That's all that means. It's the surface of one of these. Pick any one of these, and then, so that's pick a value of R, and then pick a value of T, and that's what you have here. And this is just what it looks like at different times. Okay, so this would be R1, R2, R3, and this is just picking one R and then moving it along T. Okay, clearly drawing different R's at different times just becomes a headache. I'm not going to do it. Okay. Okay, so in that foliation, we can ask, what is the metric on an S2? So if we just fix the value of R and T, then what we're left with is a two-sphere. But we know the metric of a two-sphere. You worked with it in your homework. Okay. Do it again!
I can't stop it.
Well, he was trying to scare us.
You okay? Was it you?
Yeah.
Okay, all right.
That would
You
have
didn't scare me though. It was a nice try.
I know, I felt my wind-up was predictable. Sorry about that, anybody who peed in their pants. Okay, so on a two-sphere, the metric is just d theta squared plus sine squared theta d phi squared. Okay, this is on a unit two-sphere. And you would just scale this by a factor of r squared in normal spherical polar coordinate language. Okay, but if you're just on a two-sphere of unit radius, that's what the form of the metric looks like. And so, because we're assuming this foliation in terms of these two spheres, we immediately get to conclude two things about our unknowns. The first thing we get to conclude is that there is no g theta phi cross term. Okay? Because you're building the whole solution out of two-sphere metrics, and two-sphere metrics only have d theta squared and d phi squared. They don't have a cross term. And you know that there's no further dependence on theta or phi. Okay? The only dependence on theta in the whole metric is actually that term right there, which is just part of the usual two-sphere metric. But whatever appears in the rest of the metric should not depend on theta and phi. All of this is just a consequence of spherical symmetry. And it's very similar to the way we started the electric field story. Okay, we said that the function, the electric field, would not depend on theta and phi. Okay? All right. So that's the first thing that we can do. And then the second thing we can do is we can say the following. If we want, so on one sphere, I have this metric, d omega squared. So I've got some theta and phi. And that's defined on one sphere at a time. If I take two of these layers of the onion, then this has its own theta prime, phi prime, or actually I should say its own set of labels theta and phi. And then I want to do something very sensible, which is to say, and the difference of course is that while this one is at R1, this one is at R2. They're at different values of the radius. So I want to do something sensible, and that is to say, if I take a radial trajectory and it hits the first surface at a value of theta and phi, then I want it to hit the second surface at the same value of theta and phi. Okay? That is, so what we're doing is we're aligning all of our spheres so that a radial line punctures the same value in theta phi on each layer of the onion. That you could ever not do that might seem weird. It's almost something you would have assumed. Okay? But it's a flexibility you have to not choose this, but we're going to choose it. Because if you choose it, then what it means is that moving in the radial direction doesn't influence where you are in the theta phi. Similarly, you can move in the theta phi, and that doesn't change where you are in the radial direction. There's no cross-contamination between radial motion in the geometry and angular motion in the geometry. Does everybody understand that? Because I'm about to write down the consequence. The consequence of that is that the cross terms between the radius and the angular coordinates have to be 0. Okay. Similarly, if I take the spheres as they're stacked along T, and I just pick some point on the sphere at one time T, and the corresponding point on the next sphere along the time axis, if I want the value of theta and phi at that point to be identical to the value of theta and phi at that point, that is, we want the spheres to be aligned as we move in time, then this also lets us say that the cross terms for time and the angular coordinates are 0. Yeah?
Is there a reason why you can't say that about the radial component and time component?
No. We won't need to. We're going to find reasons to get around it. Okay. Okay, so what have I done? I've gotten rid of a lot of these. So I've gotten rid of this, and this. Okay? And this guy, I know, is going to be of the form d omega squared because I'm choosing to foliate the space-time in terms of 2 spheres. Okay? So by the way, like if some crazy crackpot came along and said, find the geometry that's induced by an infinite line of mass, or of tension actually is the way you call it,
It's
but
gonna be a homework problem.
it's not going to be a homework problem, I promise. It's actually something we had to do in Physics 1. It's funny enough. But anyway, you clearly wouldn't foliate the geometry in 2 spheres. You would use cylinders, which are technically 1 spheres. But, well, they're 1 spheres, and they're stacked along the z-axis. But anyway, it's fine. You could call it cylinders. It'd be fine. Okay, so we've imposed this symmetry. The symmetry has done a lot for us. It's gotten rid. The way I'm talking, I sound like Donald Trump. It's weird. There's an inflection in my voice. I was like, who does that sound? It sounds like Trump. Oh my gosh. Okay. Anybody got a hat?
We should draw. Can we dye your hair blonde?
All right. Just with the spherical symmetry, we've gotten rid of half of our unknowns. Okay. And we've also gotten rid of 2 of the coordinates that things could depend on, theta and phi. So we've really cut the problem down in half. All right, that's a lot of progress. So at the end of it, I'm going to erase all this. Any questions about that picture? At the end of it, we can say the following. Our metric at this point can be written in the following form. And I'm just going to work with the line element. I'm not going to write the matrix. We all know if I have the line element, I can get the matrix from it. I'm going to say that this is a function of r and t times dt squared. That's the GTT term. Okay. I'm going to have the GRT cross term, which I'm going to write like this. If you look at the chapter in Carroll where he derives the Schwarzschild solution, he actually treats this cross term a little more carefully. He uses these forms that don't commute. We're not going to need to do that for our purposes, but I just want you to be aware the book will look a little bit different. And then we have the radial term. And then we'll have some coefficient function, still to be determined, times the typical metric on a 2-sphere of radius r. Okay? So our analysis has really broken down to, or simplified to, finding the functions a, b, c, and d. They can only depend on r and t. Okay? Once we find those functions, we've got the full form of our metric. Yes?
Why is there 2 in front of the b?
Yeah, that's why I was saying you've got to be a little bit careful. So, so the reason that there's a 2 is because if you wrote the a function here, so t, the c function here, and then the d function actually sits on the theta and phi coordinates, like this. The off-diagonal term appears twice because it's a symmetric matrix. You could instead define this to be 1/2, and then you wouldn't have that 2, but it's a little more natural to just think of the function as b, and then because it appears twice, it gets a factor of 2 in the line element. It really won't make a difference, as you'll see when we actually go into solving for it. Okay, so that's the sort of simplified form of the metric after applying spherical symmetry using this S2 foliation. And now it's going to get annoying. Okay? So I'm going to do this a lot, and I'm going to get a little bit quicker at it each time I go. But now we're going to start using our gauge freedom to try and simplify things. Okay? And of course, that just means making coordinate redefinitions. So for the first one, I'm going to go pretty slow. Let's redefine the radial coordinate. So instead of the r that appears in this expression, we're going to work in terms of a new r prime. And remember, a coordinate redefinition can be written as the new coordinates as functions of the old ones. That's what a coordinate change is. I'm going to choose my new coordinate to be exactly the square root of this unknown function times the old radius. Okay?
That r is not in the square root.
That r is not in square root. Okay? Now, if you had a function d of r and t, okay, you could write out what the right-hand side is explicitly. We can't do that because we don't know the function d. But if I did know it, I could write the right-hand side out, and then I could invert this equation to find r as a function of r prime and t. So this is r prime as a function of r and t, but I could invert it if I knew the form of d to get r as a function of r prime and t. And then what I would do is I would take this thing and I would plug it into my metric everywhere I see r. Okay? Now, let us suppose, and this is the part which I think you're really just going to have to pay attention to and accept. Let us suppose that we managed to solve this problem without making any assumption about d of r and t. So we would solve this problem, and at the end we would get the function d of r and t. Okay? Once we have that function, we could redefine our radial coordinate in this way, and we would get a new solution. It would look a little different, but it would correspond to the same geometry, because all we've done is change coordinates. So what we can do, and this is the part that's hard to swallow, is we can assume that we did that.
Can I just do that for like a test question?
Well, if you do it right. It's subtle, okay? So let us assume that we got d of r and t, and we made this coordinate redefinition, and now let's ask, what does our metric look like in the new coordinates? Okay? So in the new coordinates, our metric would look like the following: minus a r prime t dt squared plus 2b r prime t dr prime dt plus c r prime t dr squared And now you'll notice something cool. This coordinate redefinition immediately tells me that r prime squared is drt r squared. But that's exactly what's hanging out in front of d omega squared. So this is just going to become r prime squared d omega squared.
Should the third term have a dr prime squared? C times dr prime?
Yeah, sorry, yeah, I should be dr. Thank you. Caleb, was that your question? Yeah, yeah. Okay, so if we had solved this whole problem and gotten that function d, our metric would look different. But then we would have the freedom to say, hey, you know what? I'm going to change coordinates. I'm going to make a new radial coordinate that uses the square root of that d. And then when I make that transformation, the metric is going to take this form with no d.
Why wouldn't the r squared term change to r prime squared though?
Which r squared?
Like if you were to rewrite it completely without making that assumption, you could just say like d of r prime of t r prime squared.
You could do that, but if you do d of r prime of t r prime squared, that's going to be exactly dr of t, oh shit. Yeah, it's going to be this. Yeah. No, hold on. Oh.
I think there's going to be something weird like a function inverse.
Yeah, wouldn't you have to divide it? Wouldn't it be 1 over?
Seems easy.
Wouldn't you get d squared?
I think because when you're changing the line element, don't you redefine those functions too?
No. These functions, okay, so these functions are the same functions here. They're unknown, but they're the same functions. But the ultimate dependence on r prime can be different because r depends on r prime through this unknown function dr of t. So you're using, so if a at the end of the day, you know, was, I don't know, like we'll just say r squared, then a r prime of t would be r prime squared, but of course r prime would be drt squared, or drt r squared. So the a function changes, not because the original form changes, but because when you actually substitute in the coordinate transformation, that brings in whatever changes you're having from the coordinate transformation.
It seems like you might run into an issue if d is a function that isn't invertible. Well, is that true?
Sure, yeah. No, that's entirely possible. And d, so the metric, if it's non-degenerate, which we normally assume about the metric, then d of r and t is going to be an invertible function.
Okay.
Yeah, so I'm having a bit of a brain fart, Adrian, on your question. If I take this guy and, so if I take this thing, then I do this. And then, I lost them. And then r prime squared is this. And this whole thing if I actually plug the function d in here, and then nested that inside of the function b itself and multiplied it by this should just give me yeah, no, it shouldn't give me r prime. Yeah, I'm having a total brain fart here.
Then how do you know that it's r prime squared geometries?
Well, so without so first of all, my coordinate redefinition is saying that this quantity, which appears right there, is r prime squared. So all I'm doing is I'm taking this thing and replacing it with r prime squared.
But you replace all the other r's with r primes, and then you're like, I'm not going to replace the d with r prime. I'm just going to put r prime in where it was already r.
Yeah. Okay. Yeah. Fair enough. Okay. So I think that, and this is the part that's killing me, but I believe, and I'm just having a total fart, that is what you're going to eventually find. Okay. And therefore, you can plug in r prime here, you can plug in the r prime here, but at the end of the day, it's going to give you the same results as if you just replaced this combination with r prime squared. Okay. So, I mean, we can actually write down a fiducial function for d of r and t and actually check this by hand, but we're not going to do it right now because we got way more to get through. And then we can do it after class, or I'll do it and verify it with you on Thursday.
Why are we still able to fully assume the spherical symmetry?
What do you mean?
I don't know. I feel like if you're transforming your coordinate, there might be like things pop out.
Oh, yeah. It's because we're not making a coordinate redefinition that's screwing up our spherical symmetry. Like if I redefine r as a function of theta and phi, that would do it.
Okay.
But I'm not. I'm keeping r as a function of r and t, which is totally legit. You know, our spherical symmetry still leaves everything as functions of r and t, and we've got the GRT term in the metric. But you're right, if I did a coordinate redefinition that sort of mixed r in an angle or t in an angle, then I would be screwing up my spherical symmetry assumption.
Just quick, when you wrote down d of r prime, comma t r prime, did you, on the right hand side, did you mean to write down r squared?
No, r prime squared.
Does
So
that
they're
just
both
make
prime?
D1?
On both?
Uh,
Because would that imply that d of r prime of p is...
I'm not going to stay on this. I will figure it out and bring it back to you, but if we keep hammering on this, we're never going to get through this lecture. So I'm confused. I will get it sorted out and bring the answer to you next time. Okay? All right? You good?
Yes.
We got to move on, or we're never going to get through the end of this. Okay, I apologize for being confused. You don't deserve that. You deserve better. Okay, so having made this redefinition, my metric in these new coordinates takes this form. But now I can just say I'm going to solve the problem in these coordinates. So there's really no reason to call it r prime. I'll just go back to calling it r, because it is the radial coordinate. There's really no need to give this a special name. So if you're more comfortable, you could have started the whole story calling that r prime, and then when you do this redefinition, you transform from r prime to r, and then it looks like this. I'm not going to keep primes around. We don't need to. So we're working with now this form of the solution, where we're working with the coordinates t, r, theta, phi, where secretly this r was the r prime after this transformation. Yes?
So this is something that if we were to go through and solve things with it, we would still have to treat that as like an r prime that we have to go plug back in to get our original radial component, or no?
Look, if I solve the problem in this set of coordinates, I've solved the problem.
Okay.
I don't ever need to go back and reference the form up here. I could if I wanted to. I could get the solution from this and then go back and say, what would it have looked like if I tried to use that r? And then I would undo this coordinate transformation, and then I would be able to press on. But there's no need to do that. All I want is a solution in some coordinate system. After I have a solution, then I can just change coordinates to any other coordinate system I want. Okay? So at this point, our metric our line element has reduced to this form, which also indicates the form of the metric. And now we're going to do this trick again. Okay? Slightly different. So this time, we're going to redefine time to be a new prime t prime, which is the old time coordinate minus some unknown function f of r and t prime. And I don't know what that function f is. It's not right now obviously related to the unknown functions a, b, and c. But I'm going to say something about what f is in just a moment. Okay?
Should f be in t prime or t?
So, another way to write that, it should be t prime. Another way to write that, and so I agree with you, it's kind of a circular definition, but another way to take this and rewrite it is like this, okay? Which, if you like, you could invert this to find t prime as a function of r and t, and then take that and plug it in here to find what this function looks like in terms of t. But it turns out it's going to be more useful to use this function as a function of t prime, and you'll see why in a minute. Okay? So, but at the end of the day, this does look weird because normally we write a coordinate transformation. The new coordinate is a function of the old coordinates. Okay? This doesn't look like that because it's kind of mixing the old t with the new t. Okay? But you could get it into that form if you really wanted to, by doing the inversion and then plugging in this for t prime. We just don't need to do that right now. We're going to use it in this form. Okay, so if I take this thing, then I can now start calculating the things that end up going into my line element. In particular, there's a dt term. Okay? And I'm just going to arrange this in a slightly more convenient fashion. Okay? But of course we know that our metric is going to need a square of that, so we're going to square it. So just square it out. You have this squared, you have this squared, and then you have a cross term. Which is only looking uglier okay? And now we're going to take this and we're going to plug it into the metric there, and we're going to plug it in right there. And then we're going to assume that we're replacing t in all of these unknown functions with this expression. Okay? So at the end of the day, let's see, get around for this. We're going to take a minute. All right, so we're going to have minus ART prime. So this t I'm going to replace with this thing. Okay? I'm just going to call it a function of t prime. Okay? In principle, this is, so in principle, this is a different function. We could call it a prime. Well, we'll call it a total. Okay, what do I mean by that? So if I take AR of t and say this function was t squared, and I write this as AR of t prime, then that's actually t prime plus f of r t prime quantity squared, which is a different function of t prime than this was a function of t. Okay? So just bear in mind, when I plug in the transformed t to make this a function of t prime, the total functional form as a function of t prime itself could be different. So I should give this a different label, but I'm going to be lazy and not do that. Okay? At the end of the day, we don't know what the hell the function is. So let's just call this thing our unknown and move on. Okay. So then we got to plug in our dt prime squared, and this is where this expression gets incredibly nasty. But here we go. So all of that is multiplying this term. And then we've got the cross term here. Again, I'm going to replace the t there with this expression, and then I'm going to replace the dt there with this guy there. Let me see how I've got it organized here. Yes, we'll do it this way. df dr dr squared. So this guy is dr, but then this whole dt gets multiplied by another dr, so that's going to give me dr squared. All right. And then I got this guy. Okay, so that is obviously a much simpler form of the metric than what we had a few minutes ago. I'm just kidding, it's horrible looking. Okay. And you might be scratching your head. Why did you do that, Flournoy? What was the point? Okay. Well, here's the point. I haven't yet completely specified this coordinate transformation. Now, I could pick this f to be anything I want. This is a coordinate transformation. Well, I can literally pick any f I want to go here. And that's a coordinate change. But what I'm going to do is I'm going to figure out a particular f that will make this term 0. Because if this term is 0, I don't have cross terms. Because the cross term is sitting right there. Oh, sorry, hold on, no, that's not what I want to do, sorry. No, sorry, I'm going to pick an f so that my cross terms vanish. Okay? So let's see how that works. Oh boy. So I'm going to go over here. All right, so if I collect the dr dt prime cross terms from this thing, okay, then I'm going to have 2 times minus ar t prime partial f partial r. So I've got one from this times this, and then I'm going to have one from this times this. Okay, so in this expression for the line element, this is all of the cross terms dr dt prime. Now I can say what I was saying earlier, but incorrectly. Now what I want to do is pick an f so that the thing in parentheses vanishes. Okay? So this thing vanishes for a function f of r and t prime such that the partial derivative of f with respect to r is the unknown function b of r and t prime over the unknown function a of r and t prime. Okay, I mean, you can see that. If this is that ratio, then this thing trivially cancels. Yeah, hands cross America.
Why can't you just choose a negative t prime or something?
Why can't I choose...
For the other part, using the 0.
Sorry, say that again?
So you have 1 plus partial of f with respect to t prime.
Oh,
Why
here.
can't you make that 0? If it's an arbitrary function.
Good question. If I choose the,
Would that just make every like other term 0?
yeah, I think that's gonna make a lot of stuff vanish.
That's also saying that your coordinate transformation is t equals 0,
Yeah,
which,
yeah, there's a host of reasons why I don't wanna mess with that term. Ryan, did you have a question?
That was my question. I was thinking better.
Yeah, the other thing is that, again, these are unknown functions.
yeah.
And so if I solved the problem in its current form and found A and B, I could go back and say, well, this is the f that I would need. All right? At any rate, if I choose an f of this form, then clearly this term vanishes and my cross terms go away. But this, of course, implies that f of r and t prime is just going to be the integral of this ratio plus some possible pure function of time. Okay, because the partial derivative of this with respect to r will vanish. Okay, now if we assume that we choose an f of this form, and again, like, we're projecting ahead to, well, I solved the problem and I get the functions b and a, and the metric is going to look really gross, it's going to have mixed terms, but then I can go and make this coordinate transformation using an f defined in terms of b and a like this, then I can say, what would the metric look like with that nice new set of coordinates? And in that nice new set of coordinates, our metric is going to simplify significantly. And let me see if I can write this down in an efficient way. Turns out I can. No, I can't. Okay. Oh, man. There. So my metric is going to end up taking the following form. So all of that is going to be my dt prime squared term. And again, this is just taking all of these results and plugging it back into the expression I erased. And actually, yeah, I'll do it this way. And all of that is my dr squared term. Okay, and then I've just got my little r squared, the omega squared term out at the end. Okay. And again, assuming that we just made the right choice in the first place and called this new time t prime t, we just drop the primes. There's no reason to hang on to them. So drop the primes everywhere on the t's. Okay? And there's one more. Oh, yeah, sorry. There's one more right there. Okay? And if you squint your eyes at this for a minute, you'll realize something. Okay? You have some freedom in defining f, and then there's the unknown function a hiding in here. Down here, there's this unknown function b, and there's this unknown function c. Altogether, though, this entire coefficient is just some big-ass unknown function of r and t. Yeah, I mean, yeah, if you solved it in the form that it's written right now, you would find the functions a and b and c, but then you could multiply them all together and you could just call this one big function of r and t, which I might as well call grr as a function of r and t, because it's the thing that sits in front of dr squared. Similarly, this big ass thing right here, which is not so big ass compared to that, but still, it's pretty big ass, is GTT as a function of R and T. Yeah?
Maybe this is a naive question, but what is the point of doing all of these steps? You kind of know that you can jump to, like, is it getting rid of the cross terms? Is that the main point? Because all the other ones transformed very trivially besides the cross term. You kind of see what I mean? If it's invariant under any coordinate transformation, why can't you just kind of say, oh, I know these are going to be arbitrary?
Because of what I'm about to say. I'm about to take this explicit form and actually make one more useful comment from it. Okay? So there's 30 seconds or less. Okay, so going back to our original starting point in this entire story, one of the things that we can say is the following. Oh man, okay, so I'm gonna get rid of this. Need it. Our metric is unknown, but we can say at least one useful thing about it, and that is that it's describing a space-time, and we can assume the signature of the space-time. That is, if you're in flat space, the signature is -1, 1, 1, 1. If you're in a curved space, this element, whatever it is negative, and these elements are positive. That fact won't change. The signature of the space will not change if you go to curved geometries or if you go to different coordinate systems. Okay? Now what that means is that in our description in terms of the line element, the signature is saying that AR is a positive function and CR of t is a positive function. Okay? That's why I actually explicitly put the minus sign there. Okay? So whatever this function is, it's got to be positive in order to preserve the signature of the metric. Time has to behave like time. And then this thing has to be positive to preserve the signature of the metric. Okay? Now watch this. We've done a lot of really complicated redefinition substitutions, but if I look at this term, A is positive, this is a quantity squared, it's positive, so this total unknown function is positive. Okay? That's the conclusion that you can draw by getting to this unknown function through this series of redefinitions. You can say something definite about its sign.
Could you not do that if you redefine it as GTT?
Not necessarily. Okay? Here too, you know, that thing in parentheses is really just minus b squared over a plus 2b squared over a plus c, which is of course just b squared over a plus c. Okay. But if a is positive and c is positive, clearly b squared is positive no matter what the function b is. And so we can also conclude that this guy is positive. Okay. So what we can do to enforce this, and this is a nice way when you're solving differential equations to enforce that the solution has to have a particular sign, is we can actually write these unknowns in terms of exponentials. So at the end of all of this, what we can say is that our metric is going to be minus some exponential function times dt squared. The benefit of using an exponential is that no matter what that function alpha is, that quantity is positive. Okay? And then another different exponential in front of the dr squared plus r squared dm squared. Okay? Okay. So, I know. So, does everybody understand this point about using the exponentials?
Why is it two alpha together?
For funsies.
It's just going to make so the 2 is arbitrary, alpha is an unknown function, so you can solve for alpha or 2 alpha. Okay, but what we're going to do next, which we're going to do next time, what we're going to do next is we're going to plug this thing into Einstein's equation, r mu equals 0, which means we have to calculate the Ricci tensor, and the 2's are just going to simplify expressions. Okay. All right. Okay, so we got through steps 1 and 2 of the process. We've applied spherical symmetry. We've made use of coordinate redefinitions. Basically, we used a redefinition of R and a redefinition of T, specifically chosen to eliminate the cross terms, okay, and to impose the spherical symmetry. And we've been able to reduce the metric, the unknown metric, to this form where you'll notice there's basically 2 unknown functions. Okay? So we have 2 unknown functions of 2 variables. Not terrible. So far, we have still not used this equation. And that is the thing that we're going to do next at the beginning of the next lecture. Okay, so we'll stop there for today. Where did I think I was going to get through 3 more pages for this?
3 more pages?
3 more pages.
Yeah, that was
All right.
that's some hubris right there. Well, you had been derailed by Adrian. How many pages did you get?
Yeah, Adrian, that's one question. So here we go, Adrian. You can leave if you need to, but I'm going to figure this out.
How long will it take?
I don't know, take a minute.